So I'm going to highlight our goal and then start with a sketch. So at what rate is the searchlight rotating? And I'm going to stop there. So our goal. And we want to know the rate of rotation. And if it's a rotation, that's theta. So we want to know how the angle is changing with respect to time. And we're told when the man is 15 feet from the path closest to the searchlight. So before I put X or Y or Z here, let's draw a picture so we can get our variables straight. And so I'm going to draw the light here. And so there's a beam of light, going off in this direction. So that's light going off in that direction. And let's sketch the rest of my triangle in. And then here's a path. That's where they're walking. Oh, excuse me. Path. So here's the man walking in this direction along this path. And basically, as they're walking, the light is shining on them. And that's what's creating this other part, or the hypotenuse of the triangle. This is the light shining towards them. So, oh, wow, my pen is really bad right now. So this is the light. So I want to know this angle of rotation, how it's changing. So this is my theta. When the man is 15 feet from the point on the path closest to the searchlight. This is the point on the path closest to the searchlight. So I'm going to label that. Oh my God. That's right here. So when X equals 15, if we let this path be our X, this our Y, and this our Z. And I usually label triangles that way, where the vertical is Y, the hypotenuse is Z, and the horizontal is X. Your book or other examples you might find on the internet will probably use different labeling, but it's the same math with different labels. So we want to know d theta over dt when X equals 15 feet. So let's relate these quantities. And actually, I left one off. The searchlight is located on the ground 20 feet from the path. So this distance here is 20 feet. So this here is 20 feet. Okay, so how can we relate these quantities? I want to relate an angle, and I want to relate this path, and I want to relate this side. Already, I hope alarm bells are going off in your head and you're thinking, wait a minute, that's tangent, because we have an opposite side and we have an adjacent side. And that's exactly what we want. We want to use tangent. So we know that tangent of theta equals opposite over adjacent. And in this case, our opposite side is X, and our adjacent side, this isn't going to change. X is changing because this person is walking in this direction, so this distance is changing, but the searchlight is not moving. It's like if you're walking in your neighborhood past a light, the light doesn't move, you move, so this distance here is fixed at 20, so I'm going to leave this number here as 20. So let me rewrite this. Tangent of theta equals X, should we just go ahead and multiply 20 to both sides to get 20 tangent theta equals X. And now I'm going to use implicit differentiation to find the derivative of both sides. So we have 20 times secant squared theta times d theta over dt equals dx over dt. The derivative of x is just 1. And then since we're taking the derivative with respect to time, we need to multiply by dx dt. And in case you're still wondering at this point, the reason we're taking derivatives is because we're trying to figure out or relate quantities that aren't changing, like say this here, to rates of change for quantities that are changing, like this angle. And the only way to relate these quantities that change and don't change is by using derivatives, because a derivative by definition is the rate that one quantity changes with respect to another. Okay, so let's see what we found by this derivative. We found our goal. Our goal is right here. That's nice. So let's rewrite this. So secant squared theta d theta over dt equals 1 over 20 dx over dt. And if you notice, all I did was divide both sides by 20. And now let's rewrite secant squared, because secant theta is equal to 1 over cosine theta. So I'm going to erase this here, and I'm going to rewrite this in terms of cosine. So let me erase this. This becomes 1 over cosine squared theta. So hopefully that makes it a little bit easier to see what I'm going to do next. And let me hide the problem so I have more space to work. D theta over dt is equal to cosine squared theta over 20 times dx over dt. All I did was multiply both sides by cosine squared. So we know what dx over dt is. Let's go back to the problem. The man is walking along a speed of 4 feet per second, so that's dx over dt. And I was pretty bad here. I didn't label it originally, and I've been pretty good about labeling things before we start the problem. So dx over dt is equal to 4 feet per second. Now, what is cosine in that case? Because we don't know what cosine is, but we can figure that out. So let's look at our triangle. And again, we're told that our goal is to find this rate of change when x equals 15. So I can relate all these using the Pythagorean theorem. And maybe I should add a certain label to my triangle, not to scale at all, because this distance we're saying is 15 and this is 20. So this side should be longer, but I drew my picture a little bit poorly. So not to scale. So x squared here is 15. So we have 15 squared plus y squared is 20 squared equals z squared. With some algebra, we get z equals the square root of 15 squared plus 20 squared. So z equals the square root of 625, which is just z equals 25 feet. How does that help us, knowing that this distance here is 25? Well, now we can find what cosine of theta is, because cosine of this angle is adjacent hypotenuse. So let's write that down. So using this, cosine theta equals 20 over 25. Ooh, why did I write 205? That's not good. 25. And that reduces as a fraction to 4/5. Wonderful. So now we can write d theta over dt is equal to 4 over 5 quantity squared. That's because cosine of theta is squared, times 1 over 20 times dx over dt is 4. So we have 4 squared times 4 in our numerator, and our denominator we have 5 squared times 5 times 4. And in case you're wondering where I got these from, 20 is 5 times 4. Here's this, so 20 is 5 times 4 here. This 4 is here. And this 4 squared is in the numerator. This 5 squared is in the denominator. And the only reason I do that is because this makes it really easy to quickly compute this without a calculator. These 4s go away, and we end up with 4 squared over 5 cubed, which is 16 over 125. And if you put that in your calculator, we see that d theta over dt is equal to 0.128. And then red over here, I'm going to write this out in a really clear way. The search light is rotating at 0.128 radians per minute. Oh, wow. I'm going to do my best to try to get a new Apple Pen this week at 0.128 radians per minute. And let me zoom out so you can get a good picture of everything in this problem that's going on. And for those of you still watching, I'm going to stop my recording now.